All right, welcome to section 10.1.2. In this section, we're going to be looking at some basic probability. So we're going to have some definitions, and then we'll do some experiments and looking at some things. So first, with our basic definitions, it says each repetition of an observation of an experiment is called a trial. So every time you do an experiment, just like science, you call it a trial. Each possible result is called an outcome. And then the sample space is a set of all possible outcomes. So those are three definitions there that we will be using. All right, so helping to identify the sample space. So for the first one, if we're tossing a coin, what would our sample space be? And again, the sample space means the set of all possible outcomes. So if you toss a coin, your possible outcomes either heads or tails. That's it. Two possible outcomes, heads, tails. When we're tossing a six-sided die, what are your possible outcomes? Well, you can get a 1, 2, 3, 4, 5, or 6. So you have 6 possible outcomes in your sample space. Those are all your possible outcomes. And when you spin a spinner that looks like this, you have the numbers 1 through 8 as possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. As we go down to the next row here, if we're tossing 2 coins, now what are our possible outcomes? Well, we could get a head and a head and a tail and a head, or a tail and a tail. Think about what your possible outcomes are for rolling a coin and then tossing a coin and then rolling a six-sided die. How many possible outcomes do you have, and what are they? So here we can get a head with the numbers 1, 2, 3, 4, 5, and 6. We can also get tails with the numbers 1, 2, 3, 4, 5, and 6. So that's our full sample space, and there are 12 possible outcomes here. For the last one, tossing a coin and spinning the spinner, we then have head with all the numbers 1 through 8 and tails with all the numbers 1 through 8. So in this case, we have 16 total possible outcomes in our sample space, but we have the entire sample space right now there. So again, sample space is the set of all the possible outcomes right now. A couple more definitions. So an event, when we talk about an event is an outcome or a set of outcomes. Probability is defined as the chance of an event occurring. Probabilities can be represented as a fraction or decimals between 0 and 1, or also percents between 0 and 100. So you can always write probabilities fractions, decimals, percents. So if I write 1/2 and you write 50% or 0.5, they're all correct. If we look at this number line on the bottom, kind of just showing what we have. So something with 0% chance of happening is totally impossible. No shot of happening. Okay. Something that is less than 50%, obviously we would say that'd be unlikely, but it is still possible. And the closer you're getting to 0%, is becoming less and less or more and more unlikely. So something like 2% is more unlikely than something like 40%. Right at 50%, we call that as likely to happen as not, because at 50% chance, you have half the chance of it happening, half the chance of it not happening. Between 50% and 100%, we'd say that's more likely to happen. And again, the higher you get to more towards 100%, the more likely it is. So something like 90% is more likely to happen than 55%. And then at 100%, it is absolutely certain to happen. Not even a small chance that it's not going to happen. 100% means it's absolutely certain going to happen. So as we look here on the next page, we're going to write the words impossible, unlikely, as likely as not, likely, or certain to describe each of the events. So it says there are 31 days in August. Well, there are exactly 31 days in August every year. So this is absolutely certain to happen. So we'll put a C here for certain. Amelia correctly guesses a number between 1 and 100. So if it's a total shot in the blue, there's a chance she can get it, but it is very unlikely. So we're going to just write U for unlikely. So it's in that left side of the number line. It's not impossible, but it's unlikely. A coin lands tails up. So again, what we know from a coin, it's either heads or tails. So that would be as likely as not. So I wrote Alan there, as likely as not. Noah rolls a 10 on a standard die. Well, standard die goes from 1 to 6. So is it possible to roll a 10 on one die? No. So that is impossible. It cannot happen. 0% chance of it happening. It's a better chance of you winning the Powerball than rolling a 10 on a 6-sided die. A shoe selected from a pair of shoes fits the right foot. Well, you have a left foot and a right foot, so that would be 50% chance. So we're at as likely as not here. Marissa rolls a number less than 7 on a standard die. So number less than 7 would be 6 or below. So 1, 2, 3, 4, 5, 6, which is all your numbers. So that would be absolutely certain, 100% chance. Jessica correctly guesses the last digit of Madeline's phone number. Well, there's 10 digits, 0 through 9. So the chance that you correctly guess it, it's possible, but it's really only a 1 out of 10 chance, so it's unlikely. And the last one, Patrick pulls a red card from a standard deck of cards. Well, if you know a deck of cards at all, there's red and black, half red, half black. So it's as likely as not. All right, as we go into experimental probability, experimental probability says you can estimate the probability of an event by performing the experiment. The experimental probability of an event is the ratio of the times the event occurs to the number of trials. So this P represents probability and E is the event. So whatever the probability of the event is. So we would say on the numerator, number of times an event occurs. And then the denominator is the total number of trials. So it says an experiment consists of rolling a die 100 times. Use the table below to record the results. And then we're going to use that table to help calculate these experimental probabilities. So on our graphing calculator, we can actually roll a die 100 times pretty easily. I'm going to go to apps here, and you don't have to do this. You can just follow along. 8 is probability simulator. We're going to toss or roll a die. And we're going to roll by pushing that button. And I'm going to do 50 then. So I'll do plus 50. So up to 51. 61. Now I got to get up to 100. All right. So all right, for a 1, we have 23. And a 2, we have 16. 23, 16. For 3, we have 11. 4, we have 16. And again, this is an experiment. So if you did this on your own, your results would probably be different than mine. And then 5 is 14 and 20. And if this was perfect, we know the probability of all these numbers should be even. So what it says down here, it says with probability, the more trials performed, the more accurate the estimate will be. Experimental probability can be used to make predictions based on accurate information. So if we did this like 1,000,000 times, we should see that these numbers should all be very close. Because again, in actuality, they all have the same probability of coming up. All right, so those are our results here. If we look at our numbers here, it says an experiment, or we're finding the probability of a 3. Well, for a probability of a 3, in our experimental probability, we have 11 out of the 100. So 11 out of 100 is our experimental probability for this problem. Again, if you wanted to put it as a decimal, you could do 0.11 or 11%. Probability of an even number. So my even numbers are 2, 4, and 6. So I had to add those all up. So 16 plus 16 plus 20, we have is 52 over 100. So that's close to being 50%. Like it should be 50% in theory, but it's close. So 0.52 or 52 over 100. A prime number. So prime numbers are numbers that cannot divide into itself prime numbers are numbers that cannot be divided by anything other than itself and 1. And by definition, 1 is not prime. So our prime numbers are 2, 3, and 5. So again, it really should be 50% chance of happening because half the numbers, but if we add these all up, we'd have 16 plus 11 plus 14. So we have 41. So that's a little bit lower than we would expect. All right, number greater than 3. Again, number greater than 3 would be 4, 5, and 6. So again, that should be it's half the numbers. In this case, it is actually half the numbers. So if I add 16 plus 14, I get 30 plus 20 is 50. So I actually get what I expected here, 50 over 100, or 1/2, or 0.5. And then anything not prime, so this 1 is not prime, 4 is not prime, 6 is not prime. So I get 23 from 1, 16, and 20. So I get 59 over 100. So again, experimental probabilities is when we're actually doing it and getting our probabilities based off our results. And again, like I said here, the more times we actually do it, the closer our experimental probability will be to our theoretical. So again, we'd probably want to do this maybe, a couple thousand, if not million times to get it really, really, really close. All right, as we go to some practice here, it says a manufacturer inspects 800 light bulbs and finds that 796 have no defects. What is the experimental probability that a light bulb chosen at random has a defect? So anytime we do probability, we write this P for probability. We're trying to find the probability of a defect. So 796 of them had no defects, which means 4 out of the 800 had a defect. So we write 4 out of 800. Now we do want to either reduce that, and to reduce that on our calculators, remember we can do 4 divided by, oops, sorry, I gotta get out of here. I would do 4 divided by 800. And to make that into a reduced fraction, you press math and then number 1 for fraction. So 1 over 200 or 0.005. And you can decide which way you want to do it. Or if you wanted to write it as a percent, you move your decimal 2 places, so it would be 0.5%. The manufacturer sends a shipment of 3,000 light bulbs to a retailer. Predict the number of light bulbs in the shipment that are likely to have defects. So we know that 0.005 of them are expected to have a defect. So out of the 3,000 light bulbs, I'd have to do 0.005 times 3,000. So I would expect 15 of those to have a defect. So that's where we can use probability to help make predictions. All right, we also have theoretical probability. So experimental probability is based on the results of an experiment, where theoretical probability is what you would expect to happen, is the what if probability, we say. So theoretical probability, we have P of the event, and again, the way we pronounce this is probability of, in this case, event E. But we put whatever event we're trying to find here. And so the way we define theoretical probability is favorable outcomes over total outcomes. So if we look at our practice down here, it says a bucket contains 15 blue pens, 35 black pens, 40 red pens. One is chosen at random. Find the theoretical probability. So the first thing we always have to do is find the total. So if we add 15 and 35, that gets us 50. And then add to that the 40, so we have 90. So our total is 90. So if we're looking for probability of black pen, there's 35 of the 90 that are black. Now, again, we want to reduce that fraction. So if I press 35 divided by 90 on my calculator, and again, press that math fraction, that would reduce to 7/18. If you wanted to keep it as a decimal, it is a repeating decimal. It would be 0.389. All right, the probability of blue pen or a red pen. So when we're talking about ors in probability, if I want blue or red, I would be adding those two together. So my blue is 15, my red is 40. So that'd be 55 over the 90. Again, I would then do 55 divided by 90 on my calculator, math fraction, and I would get 11 over 18. Or if you want it as a decimal, 0.611. All right, probability of not blue then. So not blue would get the blues out of the way. So we're looking at black or red. So I add the 35 and the 40 together, and that would be 75 over the 90. Again, if I reduce that, 75 divided by 90, math fraction, 5/6. Which, if I made that into a decimal, 0.833. But look at the next one. Probability of black pen or not a red pen. So I'd be adding the black pen, and we don't want a red pen, so we're looking at the black and the blue. So 15 plus 35 is 50 over 90, 5/9, or 0.556. And the last one is probably a green pen. Well, do we have a green pen in there? Nope. So it's absolutely impossible. 0% chance probability because we don't have a green pen. All right, so that's what we know about probabilities in this section. We'll be working more with them in the next couple of sections as well.